Atoms, the fundamental building blocks of matter, are fascinating structures. They consist of a dense, positively charged nucleus surrounded by a cloud of negatively charged electrons. These electrons occupy specific energy levels, much like guests on different floors of a hotel. These energy levels are quantized, meaning electrons can only exist at specific energy values. Think of a staircase where you can only stand on the steps. Electrons can only occupy these discrete energy levels. The lowest energy level is called the ground state, and higher levels are called excited states. When an atom absorbs energy, an electron can jump to a higher energy level. Conversely, when an electron falls to a lower energy level, energy is released. Understanding these energy levels is crucial for how atoms interact with light and other atoms. By studying the energy absorbed and emitted by atoms, we gain insights into their structure and properties. One key concept in understanding electronic energy levels is ionization energy. Ionization energy is the minimum energy required to remove an electron from an atom in its gaseous state. Imagine trying to pull an electron away from the attractive force of the nucleus. The ionization energy represents the effort required to overcome that attraction.
Ionization energy is a fundamental property of an element. It tells us how tightly an atom holds onto its electrons. A high ionization energy indicates a strong attraction between the nucleus and the electrons, making it difficult to remove an electron. Conversely, a low ionization energy suggests a weaker attraction, making it easier to remove an electron. The concept of ionization energy provides valuable insights into the arrangement of electrons within an atom. By measuring the energy required to remove successive electrons, we can determine the number of electrons in each energy level and gain a deeper understanding of the atom's electronic configuration. This information is crucial for predicting and explaining the chemical behavior of elements.
When we examine the ionization energies of an atom, an interesting trend emerges. The first ionization energy, the energy required to remove the first electron, is always lower than the second ionization energy, the energy required to remove the second electron, and so on.
This trend of increasing ionization energies for successive electron removal provides compelling evidence for the existence of discrete energy levels within an atom. Think of it this way. The first electron removed experiences the weakest attraction to the nucleus because it's farthest away and shielded by other electrons. Once it's gone, the remaining electrons experience a stronger attraction to the now more positive nucleus, making them harder to remove. This pattern of increasing ionization energies would not be observed if electrons were not arranged in specific energy levels. If electrons were all equally attracted to the nucleus, removing each successive electron would require roughly the same amount of energy. The observed trend strongly supports the idea that electrons occupy distinct energy levels, with inner electrons more tightly bound than outer electrons.
Section 4. The hydrogen spectrum and emission spectra of elements. The study of light emitted by atoms, specifically the hydrogen spectrum, supports the idea of quantized energy levels.
When we pass electricity through hydrogen gas, it glows with a characteristic pink light. Passing this light through a prism separates it into distinct lines, forming a line spectrum.
Unlike a continuous rainbow, the line spectrum consists of specific, discrete lines. Each element produces its own unique line spectrum, an atomic fingerprint.
These discrete lines in the hydrogen spectrum provide evidence for quantized energy levels in atoms.
Section 5. Bohr's atomic model, quantized energy levels and electronic transitions.
Bohr's model introduced the idea that electrons orbit the nucleus in specific quantized energy levels. When an electron jumps from one energy level to another, it either absorbs or emits a photon of light.
These energy transitions explain the discrete lines observed in atomic spectra. Each line represents a specific transition between energy levels.
Bohr's model was revolutionary because it provided a clear explanation for the stability of atoms and the emission spectra of elements. It laid the foundation for our modern understanding of atomic structure.
While Bohr's model has its limitations, it was a crucial step forward in the development of quantum mechanics. As we delve deeper into the mysteries of atomic structure, we uncover more about the behavior of electrons and the forces that govern their movements.
So what's next? How do these discoveries impact our understanding of chemistry and physics?
The journey to unravel the secrets of atomic structure continues, with each discovery bringing us closer to a more complete understanding of the universe at its most fundamental level.
It's fascinating to think about how much we've learned and how much there still is to discover.
Indeed, the study of atomic structure is a never-ending quest, one that continues to challenge and inspire scientists around the world.